Hi everyone, greeting of the day. I am Anjali Dikshit and I'm from India. And today I'll be talking about detection of gas chimney from deep-seated reservoir present in northwest shelf of Australia using multi-attribute analysis. So before diving deep into the topic, first I would like to highlight the flow of my presentation. So here I'll start with introduction, then move to the methodology part, and then I'll summarize my presentation with my findings and conclusions. So now let's understand the technical term that I have used during my title. So first is the gas chimney. Gas chimneys are the migration pathways created by gas that are visible in seismic data. And the source of gas migration could be source rock or a reservoir rock present, or it could be generated through secondary mechanism as well. Now the second term comes is the seismic attributes, which are mathematically derived parameters that we use to get the maximum information from the seismic data. And the example includes energy, instantaneous amplitude, similarity, etc. So now the single attribute is not sufficient to capture a target body that we are interested into. So that's why in this study we incorporated multi-attribute analysis. So in that way we can capture all the features exhibited by the geobody in which we are interested. Now you all must be thinking that why such kind of study and or why understanding gas chimney is so important. So here you can see the four major implications that it will help into. So in a summary form, I can say that uh, understanding a gas chimney can be a major can add as a tool, as a value added tool into our existing E&P workflow. So moving forward, let's understand that why we conducted or why we did such kind of study. So through an extensive literature, I have found that there are so many studies that have documented well, which suggests that their gas migration phenomena has happened in this Poseidon field, and they proved their hypothesis through remote sensing data, geochemical data, or with the help of seismic data. Also, there is a uh, well documented the presence of deep reservoir present in this area. But one thing which is missing is how the migrating gas features are related with the deep reservoir, or how or what is the spatial extent of this migrating gas, and how these are connected with the from the starting from the subsurface to the seabed. Let's understand about the Poseidon field in little bit detail. So here you can see the location of the Poseidon, where it lies in the central part of Browse Basin. And this is the lithostratigraphy framework of the Browse Basin, where and out of all these formation, Plover formation is the target formation for gas exploration and production, which is a fluvial delta stack formation. And this complex lithology is formed as a result of 6 major tectonic activities, which majorly includes extension, subsidence, and inversion. So to achieve the stated objective, we have categorized our workflow into 4 categories. First is data conditioning, so to remove the noises and to smoothen the data. Second, we did the attribute extraction to capture specific features of gas chimneys. Then we move forward to the NN implementation. So to combine all the extracted attributes and produce a one single attribute that will specifically tells about the presence of gas chimney. And then finally we use two validation technique to validate the results of NN training. So in the first part, data conditioning, we applied dip azimuth computations. So what dip azimuth does, it highlights the local dip or azimuth variability. And here for this specific channel, you can see the high dip values, which indicates that the reflectors are not continuous in this whole region. And then later we applied the second segment of the data conditioning, which is structure oriented filtering. So this image A is the image of original seismic data and B is the image of same seismic data after applying the filtering. And here you can see a significant change. So now the demarcation of, or now the highlighting the features related to gas chimneys are very easily available. For example, bright spots and the push down features. So after getting the noise free data, or after removing the random noise, we move to the second segment, which is the attribute extraction. And as I mentioned earlier, that during attribute extraction we try to capture the major signatures of gas chimneys. So, and that includes vertical nature, chaotic or random texture, low amplitude and frequency, and the final is low similarity. So to capture each of the signature, we have used a few set of attributes. And here are the response of few attributes. So for example, let's see signal to noise ratio. So here you can easily identify we are getting very less signal to noise ratio, which are indicating the presence of gas chimney in this particular area. And similar pattern we got for other attributes as well. Moving to the third segment of our workflow is the NN implementation. So that we did to combine all the extracted attributes into a single meta attribute that we call a chimney probability cube. So here you can see that we used, in the study we used 6 major attributes, which combined with the help of hidden layer, which consists of 11 nodes through a complex technique. And in this neural network it used back propagation technique, and as it's a supervised classification, so we provided few pick sets like which were picked manually. And here here you can see the yellow dots are highlighting the area where the chances of gas chimney is high, and the pink dots or the magenta color dots are highlighting the no gas chimney zones. So after combining these two, or after providing these points as a training for neural network to train itself, we got chimney probability values. And here you can clearly see that these yellow regions are showing the probable gas chimneys areas. So to validate, then we check the obtained result with the help of statistical parameters. So in this case, it's normalized RMS error and the misclassification. And here you can see that we're getting a uh, pretty good number of RMS, pretty less RMS error, which is around 0.25, and a very less number of misclassification. And the same thing is also visible through confusion plots. And here is the final list of all the attributes corresponding their weights that the NN have used. So finally, if we validate our result through geology or the geological features, so it is matching pretty well. And after getting this satisfaction, we produced a 3D model of the gas chimney, and here you can see the how the gas clouds is coming from a targeted reservoir, which is a pro formation, how it is cutting through the um, major horizon that we have picked. The first one is the Jameson and the Johansson, and it's coming up to the seabed. And again, to get the more level of confidence for our obtained gas chimney probability, we did we did we created horizons. This first horizon is for a Jameson formation, and the black, and this is plotted on, like, it is showing the similarity attributes, where the black patches are showing the patches of low similarity, and the corresponding, and now the figure B, you can see a it's a co-rendering of created or the process chimney probability. So you can easily identify that where the similarity is low, we are seeing the perfect overlap of green patches. The same process we did for the seabed, and here the uh, black color is indicating the poke marks, which is matching well with the geometry as well. And when we overlaid the processed chimney properties, perfectly matching well, so it gives more confidence to our interpretation. So in a, and to validate this result, we have used two techniques. First is the spectral decomposition, where we checked a result with three different frequency, and for spectral three different frequency, that is 35 Hz, 25 Hz, and 15 Hz. And for spectral decomposition, we have used CWT technique. So here you can clearly see that for highest frequency, that is 35 Hz, we are able to see a maximum attenuation corresponding to the gas chimney. So which again supports the fact that the neural network have highlighted the results are very much convincible. Second technique that we have used to validate an end result is the crossplot, and I'll say it's a very innovative way to validate this result. So here we have used a lambda rho versus gas chimney probability crossplot, where lambda rho is calculated from a well-logged data that we we had. And for calculating lambda rho, we have used bulk density log data, compression DTCO and DTSML data. And here you can again, and the color of the dots are represented by the P impedance. So for the region of low gas chimney probability, we are getting a high value of lambda rho, also also a high value of P impedance, which is clearly indicate that these zones are not like characteristic features or characteristic of a gas zone. But when the gas probability is getting higher or above 0.5, we are getting a zone where the P impedance is very low, which indicates that yeah, it could be due to the gas. And the second thing is that lambda rho values again is very less. Also, on top of that, the probability of gas chimney which we get through our NN training is indicating very high probability. So this zone is fulfilling all the three criteria, and we can characterize this particular zone as a gas zone. Summarized manner, we can say that data conditioning is very much essential because it highlights the hidden features present in the seismic data. Second thing, meta attributes can do wonder. It make your interpretation more easy or more robust and much more reliable, because here when you are using artificial intelligence which give you a flexibility to combine as many as attribute that you think are important to highlight your target geobody. Third thing, that the complete 3D extent or the 3D view that we get out of this chimney probability view is very much important or very much accurate to predict the extent of gas chimney, which gives the idea of that where are the gas pockets available, and which will help to decide the drilling plan accordingly to mitigate the hazards. And the final thing that we can conclude through this study is that as the seabed we can see the poke marks, and our gas chimney results are perfectly matching well with the poke marks or the seabed feature. So it suggests that it's an active sea system. So that's why the gas is was able to reach up to the seabed. So with that note, I would like to